Thank you.
Hello, good afternoon. My name is Amalaye Oyaki, and I am a spacecraft flight software developer at Blue Origin. I will be presenting on the Space Robotic Operating System, also known as Space ROS. Space ROS was announced at ROS World last week by Dr. Kimberly Hambuchin, and Space ROS is a collaboration between NASA and Blue Origin to develop an open source robotic framework for space applications. Many of you may be familiar with the robotic operating system, otherwise known as ROS, which is widely used in academia. And so ROS provides a lot of robotic functions and applications and is an open source framework that's very widely used. What we are doing is taking the ROS2, the most recent version, and maturing the code base of ROS2 to make it suitable for use as spacecraft flight software. So that's our objective, to take ROS2 and use it as spacecraft flight software. The intent is that we will produce an open source framework that will be suitable for robotic applications. As part of our approach, we will be developing a continuous qualification framework that will produce verification results during every step of the development process. So if you think of continuous integration, continuous qualification will be the next step forward. And the intent is that it would be widely adopted within the space community. Thank you.
Hello, everyone. Okay, thank you. So my name is MD Rahman. I am an assistant professor at the University of Texas at El Paso, third year. This is a NASA Luster granted project where we are working on developing advanced thermal mining technology where we can collect 1 kilogram of ice in 11 hours with some technical tuning. Now think that if we don't do those tuning, these collections will be 10 to 20 times lower. Now, what are the tunings we are dealing with? So we have 3 tunings in here. The one is, so the sublimated vapor is very low pressure, it's under the vacuum. So we are ionizing the vapor molecules and transporting them to the cold plate using an electrostatic field. So that is our one addition to this technology. And now, once the vapor goes to the cold plate, now we are continuously growing the ice. So ice is growing, heat transfer goes down, we collect less ice. To address that, we have created a thin lubrication layer, vapor lubrication layer, by heating the ice between the cold plate and the bulk ice. So we are periodically delaminating the ice from the cold plate, and that increases the total ice collection rate. And the third one, we are developing an additively manufactured microengineered cryogenic heat pipe, and which can take the heat from the incoming vapor and reject to the lunar ambience. Yeah. Okay, sounds good. We have a poster here, and you are welcome, so we can talk more. Thank you.
Hello, my name is Elijah Cobb. I'm a research assistant at Michigan Technological University's Planetary Surface Technology Development Lab, which is named HuskyWorks. At HuskyWorks, we focus on developing technologies for in situ resource utilization. Recently, HuskyWorks received a Luster grant. We are developing a thermal model to characterize the lunar subsurface in search of water ice. This is done through various instruments, including a percussive heated cone penetrometer and ground penetrating radar. To enable the testing of these instruments, a small group of research assistants at HuskyWorks have developed the heavy onboard platform for lunar ISRU and terrain excavation, which we have given the much needed acronym HOPLIGHT. Although the original payload configuration for HOPLIGHT was enabling testing for HuskyWorks Luster grant, we've designed HOPLIGHT to be highly modular and adaptable as a general mobility platform. To enable this modularity, autonomy is currently being designed. First, engineers will issue high-level commands to HOPLIGHT. Then it will execute lower level commands using feedback from onboard sensors. This will ensure safe and accurate operations for any acceptable payload configuration. To control Hoplite, the same group of research assistants developed a novel ground control solution that connects with Hoplite's internal network to issue commands and stream telemetry. A plug-and-play system has been designed for logging scientific data throughout the duration of tests to allow safe and highly organized storage. Thank you for your time and hope to see you in the poster session.
Hello, everyone. I'm Shreyans Daftri, robotic technologist at JPL, and I'll be talking to you about the work we are doing on Lunar. Lunar surface exploration is seeing a renaissance, and some of these mission concepts require lunar rovers to support extremely long autonomous traverse in the order of tens of kilometers between successive stops. This puts a strong emphasis on the need to have accurate onboard global position knowledge at all times. However, planetary rovers till date have no onboard global localization capability. They have only used relative navigation. At the end of each drive, a ground-in-the-loop human interaction is used to get absolute position update. In this project, LunarNav, we are addressing this technology gap and developing algorithms and software to enable lunar rovers to estimate their global position on the moon with less than 10 meters in sunlit areas and 15 meters in PSRs. Our key idea is to use craters as landmarks. We detect craters in the vicinity of the rover and autonomously correspond them to a database of known craters mapped from orbit. As craters are ubiquitous on the surface of Moon, our approach is applicable everywhere and does not require high-resolution stereo imaging from orbit. In the poster today, we will present initial results of a planned 3-year project. This year, the work focused on development of crater detection algorithms and statistical performance evaluation with different sensing modalities such as LiDAR and visual sensing. Our preliminary results suggest that rover localization with an error less than 5 meters is highly probable. Please do come by to our poster to learn more. Thank you.
Thank you. So I work in industrial robotics at Southwest Research Institute, where we are currently looking to see if there are industrial robotics capabilities that will be a good fit to meet the current and future needs of the space industry. We've identified a number of technologies that are a very good fit. However, I'm going to talk to you about 2 specifically today: Scan and Plan and event-based cameras. Scan and Plan is a software framework that is used to process a part without necessarily knowing what that part is ahead of time. So it could be the case that you have maybe a CAD model, but you don't know that it's exactly correct, or you don't have a model of it at all. So you need to use stereo imaging to develop a point cloud. Scan and Plan then takes the inputs for that process. So things like offset, distance, angle of attack, those types of parameters, to then develop the raster paths for the robot to take to process that part according to the way it's supposed to be processed based on its geometry and orientation. The other technology I'd like to speak to you about is event-based or neuromorphic cameras. Now, this is something that comes from the autonomous vehicles world. And these cameras report back pixel by pixel from frame to frame what has changed. So the data set is inherently sparser. As a result, data processing is much more efficient and is able to be done much faster. And for the space industry, that means it can be done on a much lower power processor. Event-based cameras are particularly good at low light situations, badly lit situations, and places where the frame rate needs to be very high. So looking at things that are spinning or moving quickly. As a result, we see it as a very good fit for future applications in the space industry. Thank you very much. I have a poster over there. I'd love to talk to you more about this.
Hi, good afternoon, everybody. My name is Sean Doherty. I'm the sampler PI, which is landing on the moon in 2023. And today I'd like to talk about how we're taking our decades of planetary robotics experience, injecting new innovation and capabilities, and then applying that to mobility products for the lunar surface. Maxar actually has 6 of the 7 robotic arms on the surface of Mars, including the sample handling arm on Perseverance is the most recent example. We also have 6 additional arms about to launch in the next 2 years. Most of those are for on-orbit servicing or assembly, but also the sampler robotic arm, which will be our first robotic arm on the moon in over 4 decades. We're not stopping there, though. We really are striving to make space more accessible and proliferate these products and make them more capable. We're doing that in several ways. One is we're making our products modular. Sampler down on the bottom left here is a great example of that, where we have modular building blocks, actuators, and avionics coming together to form the robotic arm for that mission. Another way we're doing that is the middle column, these new technologies that we continue to inject into our programs, motor controllers, as well as the tipping point program with NASA for Luna. That really addresses all of the things all at once. It reduces the mass and the cost. It also helps us operate these robotic systems at night. And we're applying those to the mobility systems, all that heritage, all that technology to produce a product from small rovers to medium class rovers, or even subsystems on the rovers. And we're actually building hardware today, which is that last picture on the bottom right there. We have a test bed to demonstrate these technologies. Thank you very much.
Hi, I'm Mike Effinger, and I lead the microwave structure construction capability element within the Moon to Mars Planetary Autonomous Construction Technology Project at the Marshall Space Flight Center. Microwave sintering is one of 9 materials and process options currently under study by Impact as potential construction material for a planned 2026 lunar demonstration construction mission. The idea of microwave sintering lunar regolith has been around since the late 60s. All previous work before Impact was done with non-lunar-like applicators, which took into account microwave reflections to assist in heating the simulants. Impact has taken the next step to develop the processing protocols in a thermal vacuum chamber to ultimately construct landing pads and other infrastructure on the moon. We are currently pursuing 4 different microwave applicators and 2 different microwave sources. Industry, academia, and other NASA centers are involved in materials development, materials characterization, TVAC testing, ceramic analysis and testing, microwave modeling, systems design and analysis, requirements and ConOps development, etc. However, we are interested in other ideas as we go along to improve sintering uniformity and power efficiency. We will also be adding inline process feedback for verification instrumentation and site prep tools in the future to the system. We have generated a high temperature bakeout procedure to remove non-lunar phases and volatiles for JSC-1A. We'll be defining similar bakeout procedures for other simulants that will be shared with the NASA or shared with the simulant and technology community at large. I will be happy to expand on this in the poster session. Thank you.
Hi, my name is Marshall Eubanks. I'm with Space Initiatives, and I want to talk to you a little bit today about lunar geodesy. The moon is generally thought to be dead commonly thought to be dead, but I need to tell you that it isn't really dead, at least in places. There's very good reason to believe, with recent research, building on Apollo lunar ALSEP data, that the moon actually has active tectonic areas, small areas that have moonquakes, as they're called, and that these could be fairly severe moonquakes. I mean, that's been known since the Apollo days, but they've recently been connected to active areas, thrust faults and such things, typically about 1 to 10 kilometers in length. These earthquakes are pretty severe. If there was an astronaut near them, that would actually be a very big hazard to health if they happen to be outside. There could be meter level surface motions and smaller co-seismic motions in the centimeter level. So we are interested in this. We're interested in figuring out how to do this. We know how to do this on Earth. You instrument the area and you see how it's moving geodetically. We can do this on the moon. You can do sub-centimeter ranging on the moon. And that's what we intend to propose. And I have this area here you could look at. You can see how there's fresh boulders. That's a clear sign of activity. The boulder tracks. So all this is on our poster. And so come and come by and talk about it if you're interested. Thank you very much.
Good afternoon, everybody. This is Terry Fong. I work at the NASA Ames Research Center. This poster is focused on the Volatiles Investigating Polar Exploration Rover, or the VIPER, which is a 2023 NASA mission to send a rover to the area near the western edge of the Nobile crater on the moon to prospect for subsurface volatiles. I don't know who's running the slides. If you click on the picture of Viper there was supposed to be a video. In any case, I'll keep talking. If the video is actually shown here, you would see an overview of the rover, and of course now there's sound too. So I don't know if you're able to mute that.
The future of human.
I guess we get the video or the sound or just the images. In any case, Viper, as I said, is going to the moon in 2023. The poster is an overview of the rover that we have been developing for Viper. That includes both the hardware system, which is based around a four-wheel planetary rover design with active suspension. That includes the ability to actively adjust the overall suspension, the ride height for traversing slopes and obstacles and controlling load on the wheels. The software system, which is split in a novel way between onboard and ground software. We've actually chosen to take some of the flight software that's normally onboard planetary rovers and to run it on the ground because we have continuous communications to the Earth. And therefore, we can run some of the software on commodity higher performance processing on the ground. The rover itself is electrically powered. It relies upon batteries and three approximately 1 meter square solar arrays, which are located on three sides of the rover. The rover itself carries 3 spectrometers and a drill, which you can see in the video here. The drill is used for acquiring subsurface samples. The overall intent of this mission is to operate on the moon for about 100 days. That includes 3 hibernation periods through relatively short periods. This are perhaps 60 to 70 hours of darkness. And that's really enabled by the fact that we're operating in high latitude, high elevation environments here. During surface operations, the rover will be interactively operated from the ground. It will be operated in a manner that uses waypoint driving. And if you're interested, come to the poster. Thanks.
Hello, my name is AJ Gemmer. I'm the Chief Technology Officer at Lunar Outpost, headquartered in Golden, Colorado. And we are preparing our first rover, the Mission 1 Mobile Autonomous Prospecting Platform, shown in Figure 1, for its first mission to the lunar South Pole next December. So with our mission fast approaching, we are deep in our concept of operations and path planning tasks, which are fundamentally multivariate optimization problems. An example of this is that since the rover needs to remain in the sun for both electrical and thermal reasons, we map out a path that keeps us in the area of best solar illumination. But as you can see from Figure 2, which is an RF communications propagation map, about from 1/3 to 2/3 of our path takes us out of the area of best communications. And so autonomy can be used to mitigate this issue and is a practical application to solve our problem. Our autonomy algorithm is essentially automated waypoint driving with hazard avoidance, which requires less communications throughput than strict teleoperation. And that allows us to remain in areas that are optimal from a solar illumination standpoint, while still dipping out of and returning to areas with good communications throughput. Thank you.
Hello, everyone. My name is Larry Olua, and I am a graduate student from Louisiana State University. I have a poster here funded by Louisiana Space Consortium, and this is about using planetary construction 3D printing using indigenous materials like ISRU-based materials and mission recyclables. In preparation for the next human mission to Mars and Moon, it is important for us to have shelter habitat and other supporting infrastructures that would, support successful space exploration. And particularly our research focuses on using 3 select materials based off ISRU and mission recyclables. And our focus here is on the plastic deformation and plastic deformation detection. If you are interested in learning more about our work, my poster is to my left, and I'm happy to talk to you. Thank you.
Good afternoon, everyone. My name is Erin Hayward, and I'm on the Space Environmental Effects team at NASA Marshall Space Flight Center. As I'm sure you guys know, the space environment's extremely harsh, so it's very important to do proper environmental testing on the ground to make sure you understand your spacecraft performance. So we have the capability to simultaneously simulate many different aspects of the space environment, including high vacuum, UV and VUV radiation, thermal extremes, solar wind plasma, low to high energy electron and protons, planetary surfaces and regolith effects, and impact testing. So I like to call our lab the Mad Scientist Lab because every test we run is a little bit different and it's customized for the specific conditions needed. So we can work with you to define your environment, help figure out the problems you're likely to need to test for, create custom test fixtures and software, and perform data analysis. And we can also raise hardware TRL levels to 6, which is qualification in a relevant environment. And common tests we do are things like spacecraft charging and internal electrostatic discharge, total ionizing dose effects, material property changes under UV, and thermal performance in deep space conditions. But every mission is different, and we've done some really diverse stuff like splattering molten metal onto EVA suit material in a Leo plasma. We also set up a thrust stand to measure electric sail tether performance and other really interesting projects. You can see some of those on the right there. So please feel free to reach out to me and please come by my poster for more specifics on all these capabilities. Thank you.
Hello, everyone. You may know me as the lead facilitator for the ISU focus group, but this is a project that began over a year ago and funded through internal funding only, and the program is designed to develop technology that is to transition to industry. So what we explored here is the need to develop the ability to do telerobotics on the surface of the moon. What drove this is the need to build infrastructure on the moon. Shown in the upper left, that you can develop the infrastructure for sustained presence on the moon. Autonomy does some of it, but can't do the full deal. We need robotics. Autonomy can't do, for instance, the outfitting and HVAC and things like that for construction. So what level of autonomy do you have versus telerobotic operations? And to do telerobotic operation on the moon, one has to deal with latency. So what we address here is how to effectively mitigate the effective latency in controlling robots on the moon. The approach we took is shown in the middle, which is developing a model-mediated environment, so operating the robot through a model. This model is actually developed from data sent back by the robot itself. The data volume is really not that great because it doesn't need to be video rate. He demonstrated 3 components of it, which includes command and control shown in the lag-free XR experience with 2 operators there. We also showed the ability to control the spot robot itself, which shows we decided to use a Boston Dynamics spot robot. We controlled that with a 2-second latency, both for to and from the simulated moon. And we're very happy to say that we also controlled manipulating the environment using robotic arms with a 6-second latency. So feasibility was demonstrated. Thank you.
Hello, my name is Matthew Coons from Maston Space Systems, and going to talk about our rocket mining concept today. We worked on this together with Honeybee Robotics, Lunar Outpost, and also utilized some technology from University of Central Florida. Basically, this is a concept for high yield, low cost extraction of lunar resources, specifically water. We took a bottoms-up approach looking at how do we make a robust, high output system so that we can make it attractive to investors and kind of reduce that upfront investment from the billions level down into the low millions for getting a system up and operational and producing water. We take advantage of rockets being very, very good at digging holes and flip that into the extraction method. So with that, we're looking at being able to excavate over 400,000 kilograms of water per year from the lunar South Pole in PSRs. It's a bootstrappable system, so it can extract water and then it uses that water to power itself through fuel cells, also solar panels, and it then recycles that into the rocket engine as well. So it's very, very compact and efficient system for water extraction. This came out of looking at some of our landing pad technologies, and it's an interesting offshoot. So thank you very much, and come see us in the posters if you want more information.
To build things on the lunar surface, robots will need to use many different tools. So excavation and backfill uses buckets or ripper tools. Breaking rock would use an impact or rock grinder tool. Building a landing pad or a foundation. We designed a dual pin coupler interface to let a robot change out tools. It's similar to an excavator's quick change bucket attach system. This lets all of these tasks be performed by the same robot. You can put down excess tools just loose on the lunar surface. You can deliver new tools on later flights. Our coupler is designed to self-align. It uses a tilt, tilt lift pivot lock system that positively lifts the locks the tool in place. So I have a tool, I have a coupler, and basically the tool is hanging on there. It can clamp down and then lock, and it's robust enough once it's locked to actually do excavation. We've done rock grinders, we've done excavation buckets. It still works when covered in dusty regular simulant. In steel, the tool side weighs 400 grams. In our robot testing, we can align and change out tools in under a minute on robot. So we tested this with a 70-kilogram robot. It was able to do a pull-up, supporting itself on the tool coupler. So I'm Dr. Orion Lawler at the University of Alaska Fairbanks in the Aurora Robotics Lab. I'll be at the GatherTown virtual poster session, and I'd love to show you more examples and help get interchangeable tools used on lunar robots.
Hi, I'm Chelsea McMahon. I'm a systems engineer and former research fellow at the Open Lunar Foundation, here to talk about the history of collective innovation and how it applies to space today. So collective innovation is when open sharing of information leads to rapid technological advance. And one way the space industry has done this really well is by using ROS, the open source robotics framework, and now Space ROS as well. And ROS is awesome because it's very familiar to both academia and many other engineering disciplines. And because of that, it leads to a faster software development time, as well as a potential cost reduction of up to 40% due to code reuse. So we looked at a lot of other similar industries and other ways that we can stoke collaboration in space. And the automotive industry is very similar due to rigorous safety standards, reliance on multiple tiers of suppliers, and high level of competition between commercial companies. And one thing they've done super well is develop these open consortia where they work on open standards and open source software so they can focus on business differentiators. And if NASA and commercial industry and academia are interested in working on similar things, we have a lot of suggestions, and I'm happy to talk about them at the poster session. Thanks.
Hi, my name is Nathan Mellenbrink, and I am representing the RETHI Institute, STRI, at Purdue University, as well as Harvard University. And what I'm showing here is a robot factors approach to modular hardware. So by analogy to human factors or ergonomics. So that's a device designed for more effective operation by humans. And by analogy to that, we're interested in a device designed to promote more effective operation by robots. So you see in this video here, we have or rather, first let me draw your attention to the still image above it, which is me trying to operate a power module. This is a power module created by the AMPS project, so the Advanced Modular Power Systems group at NASA. And this is a really fiddly operation. It requires two hands. It requires first a few newtons of force and then tens of newtons of force. And this is something that robots can't do. It's difficult to do even with gloves on for a human. And so what we've done is we've made a redesign of this module such that the one input motion delivers two distinct output motions, first to eject the module, or first to unlock the wedge locks and then to eject the module. And so we've done this out of a collaboration with the AMPS project, but we think that this could be useful, this approach of robot factors could be useful for any kind of mission critical space hardware where maintenance should be possible by robots. And so we've demonstrated this here in the video to the left with a UR5 robot. It's able to successfully insert and lock the module. And that's something that previously robots were not able to do. Please stop by the poster session for more information. Thanks.
Okay, thanks very much. And we know that the moon has resources and we know that they have the potential for enabling a very robust cislunar economy. But what's next? We got Viper going in 2023 to be a pathfinder for prospecting, but then what? What do we do? So we're proposing an international lunar resource prospecting campaign because going about it this way, everybody wins. If we look at the legal issues posed by the Outer Space Treaty and the Moon Agreement, they can be overcome because we have an international cooperative group. The data we get back will allow science, exploration, and commercial interests to benefit. The same data sets will inform all. Next slide, please. And what we see then is that we have a precedent. The League and the International Space Exploration Coordination Group ran a specific action team to actually coordinate the missions to the South Pole by the various nations that form ISEG-G. And this then allows diplomacy to happen. And it also establishes cooperation because we know from history, cooperation gives you an enduring space program such as ISS, but competition does not. Apollo lasting less than 4 years after Apollo 11 landed. So the resource prospecting campaign allows many countries to participate. It is inclusive, and it also includes commercial opportunities. So by sharing the data, we inform multiple stakeholders. We actually then start to understand the reserve potential. But if NASA wants to lead this, they really need to have a program for Artemis rather than what it is now. And if anybody can tell me what it is now, I'd be happy to hear it. And again, this would allow resources to actually be in the critical path for having humans sustainably on the moon and also enabling a cislunar economy. Posters over here, or it will be.
Thank you very much. Up next, we have Atif Qureshi.
Hi, I'm Atif from Maxar. You heard from Sean earlier, and I'm going to cheat a little bit by going into detail on some of the stuff he talked about. So as you heard, we've been in robotics and space mechanisms for a long time, 20 plus years. Recently, our focus has been on productizing, commoditizing, commercializing the robotic system so that it can be more available for use by communities like the Lunar Science. Sean already talked about Sampler. That's our first or our actually second foray into this realm. It's Gen 2 Spider technology. It's taking advantage of design for manufacturing, modularity, commercial off-the-shelf components to deliver a lower cost system that does the robotics job. It's flying on a CLIPS mission 2023. In the middle is our tipping point project that he alluded to earlier, where we're developing a new kind of architecture to drive the whole manipulator from a single actuator. It cuts down mass. Instead of having actuators at every joint, it cuts down mass. It cuts down the cost of the system, and also it's more robust for the environment since all the parts that need to be warm are nicely situated at the base or inside the spacecraft. On the right, I wanted to mention our other effort we have going under the LVSAT program, where we are taking in, developing some technologies that NASA has put a lot of work into that'll hopefully come in handy with future lunar robotic projects. We have the deployable boom technology from Langley there, and the other picture I'm showing is electrodynamic dust shielding that's been developed out at KSC. Poster over here on the right, feel free to come by and talk to me about it. Happy to take questions. Thank you.
Hi, I'm Mick Farragelli. I'm the CTO of Mission Control Space Services, a Canadian space robotics software company. It's an exciting time. Commercial missions are paving the way for a new era of lunar exploration and really lunar infrastructure development. And that means we're going to need more robots doing more complex tasks and doing these things more autonomously. We all know the state of the art in automating some of these critical tasks is leveraging AI and deep learning. And these kinds of tasks include detecting objects from camera images, might be fusing data from multiple sensors and sources in order to make inferences about its environment, such as traversability or localizing itself. It could be automating tasks based on events and probabilities, as well as identifying anomalous conditions or events. But AI is, in fact, challenging to implement it on board these robotic systems because of the limited computing power, the complex software development and integration processes required to do so, as well as the verification and eventually the trust in these systems for mission critical use. So we're going to be tackling these challenges in an upcoming technology demonstration mission to the moon, launching in roughly a year from now. The mission is the Mohammed bin Rashid Emirates Lunar Rover mission. We're providing an edge computing device based on the lander that's going to process rover imagery. And our AI algorithms are going to be implemented on an FPGA on board a commercial off-the-shelf processor. That's going to be supporting some perception tasks in order to support science operation and rover navigation. We're also doing a number of ground systems as part of that. And so I'm excited to talk about it, excited to announce it. If you have any questions, please stop by our booth. And we think this is an important step in validating the use of AI in space. Thank you.
Hello, I'm Art Witulski at Vanderbilt University. I'll be talking about silicon carbide power devices for use on the moon. The motivation is that we need, for the envisioned applications in Artemis, we need about 10 times the power that are typical of space satellites or rovers. And so we need to operate at a high voltage, maybe around 1,000 volts. The problem is that there's galactic cosmic rays and solar particles in space. And so those cause single event burnout, SEB. And so you can see on the right some micro photographs of damaged events caused by cosmic rays. The problem is that this blows out the device. It's no longer usable. So we can't do power conversion then. And you can see in the middle there's a plot of the drain voltage of the transistor versus LET, which is a measure of the energy deposited in the device. And you can see this is a 1200 volt device, but the green line in the middle here is showing that the onset, the boundary where we get SEB is around 500 volts. So, so this is not going to be workable. So we have a Luster project, and we're working with our partner, General Electric, and we're going to be working with them to produce devices that are hardened to well above 1,000 volts here. So that's the basic idea of the project here. If you have questions, please stop by and we'll talk more.
Hi, I am Joey Palmowski with Honeybee Robotics Exploration Technologies Group. So understanding the stratigraphy of the moon is a key component of the Artemis program. It'll be invaluable to ensuring the future success of sustainable human presence on the lunar surface. And more specifically, studying the subsurface will give us a better understanding of the gardening and the volatile distribution on the moon. So a few technologies offer the ability to study 1 to 2 meters below the surface, including our 1 meter class drill Trident, which is going to be flying on Prime 1 and Viper missions. However, Rebels proposes advancing those capabilities to 10 meters below the surface with onboard instruments. So Rebel stands for rapidly excavated borehole for exploring the lunar surface. So this combines 2 existing Honeybee technologies. One is coiled tube drilling, which is used on Redwater, which is an ISRU drill for mining water on Mars, and then Lister, a 3 meter drill which will fly on the moon in 2023. The other technology is Smart Drill, which stands for Sensing, Measurement, Analysis, and Reconnaissance Tool. Rebels works by using a drill to cut into the formation while using compressed air to clear the cuttings from the borehole. The coiled tubing is wound onto a drum and is passed through an injector feeding the drill downward while also acting as a conduit for the wiring, the fiber optics, and the tubing. The Smart tool is mounted above the drill, which includes a dielectric spectrometry probe, a near infrared spectrometer, temperature sensors, and a camera. The major advantage of Rebels is the ability to bring the instrument to the sample as low as 10 meters below the surface, and then the instruments can be activated in real time and collect data, which the drill while the drill is downward traversing. Thank you, and I will have a poster as well.
That is the end, correct? All right. Am I on? Yes. All right. Well, thank you, everyone. We are now going to break for the poster session, and We have some posters in here. We can view all of those and mingle, but if anyone would like to log on to GatherTown to see some of the virtual posters, you're welcome to go into the theater, which is just over to the side, and take a seat there and log on and kind of browse around and chat. We probably can't have too many people doing that at once, or else you're going to get feedback between your different mics. But we saw a lot of really cool technology presented here, and I don't want anyone in person to miss out on the opportunity to speak to the folks who have presented those posters. So thanks again to everyone. And after we're going to wind down around 6, but I will not reconvene at that point. So, because I'm really tired, I'm going to drink some water and sit down, and it'll be great. Thank you all so much.